Hello. Today we're going to learn about normal bending stress. Now, normal bending stress arises when a coupled moment is applied to a body. So when we apply a coupled moment, in this example, a moment that is concave upward, that moment causes our beam or our geometry to bend. One side becomes longer. So one side, in essence, stretches or is under tension, and the other side becomes shorter and comes under compression. Now, with this in mind, if one side is in tension and another side is in compression, then we know that the stresses that are distributed across this body are going to not be uniform, right? So we're going to have some tensile and some compressive stresses going through this beam. Now, how do we arrive at what the distribution of these stresses are? Well, let's think about what a moment is. A moment is equal to a force times a distance, right? If x is our neutral axis, so if x is our neutral axis of our geometry, we're applying a moment to it, then in essence, what's happening is as we're moving at a distance from that neutral axis to the outer edge, the force that's distributed across this cross section is increasing. And on one side, it's in compression, and on the other side, it's in tension. And in fact, since moment is a linear equation, force times d, it's linearly distributed across the cross section. Now, let's also note that if force is distributed and the area of each of those, at a distance is changing, say we have a differential area, then we can also then say that stress is linearly distributed across the cross section. So using the flexural formula, we can come up with this distribution of stress, where depending on the coupled moment, on one side we have a normal bending stress that is maximized in tension, and on the other end of the beam, we have a normal bending stress that is in compression, right? Now, how do we calculate that stress? Well, normal bending stress, sigma x, is equal to negative our coupled moment m times y, which is our distance from the neutral axis, so where we are actually calculating sigma, divided by I, which is our second moment of inertia. Now I, in this case, where you're going to use I with respect to the x-axis, is equal to the integral of y squared times dA, where dA is a differential area that we need to solve for. And then finally, what is the maximum bending stress? Well, the maximum stress is on the outer edge, the furthest distance in our beam. In that case, it's dimension C, it's the outer edge. So sigma max, the max normal bending stress, is equal to the moment times that distance C divided by our second moment of inertia, right? So now, we've got the 2D view of the stress, but let's look at a three-dimensional view of normal bending stress. We're say, hey, we've got that same beam, but now we're looking in 3D. We have a moment that is applied about the z-axis, and if we replace that coupled moment with our stress distribution, we can see that it is linearly distributed, and it remains linear across the entire thickness of our member, right? So that means that the entire bottom of the member is in tension, and the entire top of the member is in that max compression, right? Now, second moment of inertia. Second moment of inertia is something that can be a little bit tricky to find. The core equations for finding the moment of inertia is an integral, where if it's, say, the moment of inertia with respect to x-axis is the integral of y squared dA, and the moment of inertia with respect to the y-axis is the integral of x squared dA. where dA is a term that we need to find with respect to our given geometry. So we'll actually have to determine what dA is in order to actually solve this integral. Now, when we figure out the dA element and we execute the integral for certain simple geometries, rectangles, circles, and so on, we can get the exact solution to the second moment of inertia. So for example, this rectangle, Ix is b times h cubed divided by 12, and Iy is b cubed times h divided by 12. For many common geometries, circles, tubes, triangles, and such, we can go to the appendix of our book and find the exact solution to that moment of inertia. But for complex shapes, like say we have some kind of crazy fin-looking structure or something complicated, we're going to actually have to solve the integral, right? And we'll look at some examples of that in class. Now, what happens when we have a composite shape or a shape that is a couple of different simple shapes combined together? For composite shapes, we have to determine the second moment of inertia, but with a little bit more complication. We have to apply what is called the Parallel Axis Theorem in order to join, like Legos, these different shapes and get a single moment of inertia for a complex shape. So an example here is a T member, which consists of two rectangles that have different centroids and are at a different location with respect to the centroid of the composite body. In the parallel axis theorem, what we do is we say that the overall second moment of inertia is equal to the sum of the moments of inertia of each individual element, so each rectangle, plus the area of those elements times d, where d is the distance from the centroid of each element to the parallel axes, or the centroid of our composite body. So it's the distance from the centroid of the overall composite body. So the example here for this T element, we'd simply say for element 1, which is orange, we have its second moment of inertia plus its area times d1, where d1 is the distance from the centroid of the element to the centroid of the composite body, if we consider both of these the actual center of the T, right? And then all of that plus the second moment of inertia of element 2 plus its area times d2, where d2 is the distance from the centroid of that second element to the centroid of the composite body of the overall T itself. If we are able to find those distances, calculate the areas and moments of inertia, then we get the composite, the overall secondary moment of inertia for this T-shaped geometry. So keep this in mind as you start to solve problems. If you get a complex geometry, you're going to have to apply the parallel axis theorem. And that's all for normal bending stress.